Welcome to my video course on engineering FRCS. Today we're unpacking the complex 5G core network architecture required to safely and rapidly operate digital trains. Let's dive right in and see exactly how we build the digital railways of the future, balancing intense security with ultra-low latency. Here is our agenda for today. We'll quickly cover introduction to FMCS demands, user access and profiles, network exposure functionality, low latency data routing, and finally, edge breakout with UPFs. Section 1. Introduction to FRMCS demands. Notice the massive engineering contradiction we're facing here, right? Digital rail applications like remote driving and automated train operations demand this crazy mix of heavy video transmission, absolute packet reliability, and near zero latency for things like the European train control system. But at the exact same time, the core network requires airtight security. Building a topology that actually delivers all of this simultaneously is our ultimate goal. Section 2. User access and profiles. To secure this critical network, we've got to first establish the who. Think of the Unified Data Management, or UDM, as the ultimate VIP guest list. It's the central authority in our network that strictly enforces exactly who or what gets access to our system based on rigid user access profiles. Whether it's a trackside sensor or a massive high-speed train, the UDM ensures absolutely nobody gets on the network without a verified ticket. So how does it do this? The UDM enforces these profiles by constantly communicating through very specific reference points. You've got N8 and N10 guiding the network's mobility and session management functions. Plus, it generates the vital AKA, that's authentication and key agreement credentials, pushing them straight through N13, so that every single piece of user equipment is perfectly authorized before any critical railway data is ever transmitted. Section 3. Network exposure functionality. Now that we know how internal devices are authenticated, how do outside applications securely interact with our core network? Well, that brings us to the network exposure function, or NEF. The NEF acts as a highly secure translation window. It allows authorized external applications to request network resources without ever actually touching the raw internal signaling. Essentially, it creates an isolated, perfectly managed bridge between the outside world and our incredibly sensitive 5G core. And this bridge builds a proactive defense. It is definitely not just a passive gateway. The NEF actively authenticates external apps and authorizes their requests. But look at step 4. This is absolutely crucial. The NEF actively throttles those requests to ensure our control plane is never overwhelmed by a sudden surge of traffic. It really is the ultimate gatekeeper for network stability. Section 4. Low latency data routing. With our user access and network exposure strictly locked down, we've got to shift our focus to the user plane and our massive latency challenge. Our absolute primary enemy in real networks is tromboning. That's the unacceptable latency caused by sending critical data all the way from a moving train deep back into a central core network over shared fiber links just to be routed right back out to the trackside. We literally cannot tolerate this. Instead, we have to use local edge routing, breaking out the data immediately to achieve that ultra-low latency. To prevent tromboning, we rely heavily on the user plane function, or UPF. This is our network's heavy lifter for actual data routing. While the control plane manages all the complex rules we just talked about, the UPF is down in the trenches, doing the heavy lifting of packet inspection and forwarding. So the crucial part is how the UPF connects to the rest of the network. We have N3 linking to the radio towers and N6 out to the data networks. But I want you to pay special attention to the N9 reference point. Connecting multiple UPFs together in a chain over N9 is the absolute secret to hitting our aggressive latency targets. Section 5. Edge breakout with UPFs. Let's dive into the practical application. By deploying a distributed intermediate UPF and IUPF in series right before the central PSA UPF, we can locally break out critical data directly to an edge application server. This breakout is triggered automatically by specific 5-tuple rules configured by the network. Inside that IUPF is a clever mechanism called the uplink classifier, or ULCL. Think of the ULCL like a master railway switch operator. It inspects every single incoming packet, identifies the destination, and immediately shunts that time-sensitive local traffic over to the edge server, bypassing the central core entirely. Meanwhile, your standard internet or general traffic, it just continues on its normal path. Of course, trains move, right? Because our IUPFs are highly distributed and co-located with the radio nodes right along the trackside, the core network can continuously and seamlessly hand over these edge sessions as the train flies down the track. It modifies the data path on the fly, maintaining that crucial low-latency connection without ever dropping the session. What makes this architecture truly elegant is that the train's onboard systems only ever see a single IP address. The system is incredibly complex under the hood. We're talking multiple session anchors and dynamic routing, but it completely hides this immense complexity of the multi-UPF routing framework from the train itself, ensuring rock-solid stability. Mastering the interplay between airtight control plane exposure through the NEF and UDM and highly distributed user plane routing using the UPF is really what defines an expert architect. So the big question remains, how will you architect your network to balance the strict security profiles of the UDM with the ultra-low latency edge breakouts of the UPF? Thanks, we can see you next video.